discussion that I did. So today, I hope everything is completed. So from now on, you can start using the application. So just give you a view of all Siemens CDS, what are the tools available in Siemens CDS, and what is necessary for, and the basics of some ASIC. So I think you all know about the FPGA and ASIC. You know about VLSI, right? VLSI is a very logical integration. And under the VLSI, we have FPGA and ASIC. So FPGA is a field programmable paper where you can reconfigure the hardware. And ASIC is an application specific integrated circuit where you will build your own custom hardware. So this is the difference between the ASIC and the FPGA. I will move the ASIC versus FPGA in the next slide. First, I will just introduce you about the Siemens CDS tools. So previously, the Metagraphics, what I have mentioned here, this was a separate company. Now the Siemens has taken over the Metagraphics and now we will call it as the Siemens CDS. And under Siemens, there are various tools available, not only like physical design and analog design. There are synthesis tools and even some PLMs are available. Various things are available, and even the PCB tools. And here you have EDA tools, PCB tools, both procured. Today, I will be introducing you with the EDA tools, not the PCB. So I will give you a glance of PCB also. Like that further tool setup and the demo for that will be given from some other person who handle the PCB. So moving further, so what do you mean by electronic design automation? So EDA is nothing but a electronic design automation. So EDA tools are software which are used by the engineers to design what you will do. Like whenever you do some design, you want to do the simulation through the graphical waveform only will confirm whether the functionality of your design is working properly or not. So the engineer, what he will do, he will design the things, then he will simulate. And once the simulation is done, next he will go for the verification where he will verify and he will prepare the electronic systems. And whether it's a custom chip, like as I told about the ASIC, these tools mainly comprises of the ASIC. That is the application specific integrated circuits. And today, whatever the demo we will perform, that is a Tanner and Caliber, it's a complete ASIC oriented. It's not a FPGA. FPGA is completely different world. And here, it's a whether it's a custom chip ASIC or a reprogrammable chip. Reprogrammable is a FPGA. So here, when it comes to the ASIC, what you can just keep in your mind is ASIC is not a reprogrammable, but FPGA is a reprogrammable. So you can reprogram anything under the FPGA, but in ASIC you cannot reprogram. Once something it will be built for certain application, and you can only work on that particular application using the ASIC chip. Here you will do the design from the transistor level. And in FPGA, you will not do any transistor level design. You will be having the hardware in hand. You will build the application further using hardware description language. That is HDL. So this is about the EDA. And without EDA tools, building modern electronics will with the billions of transistors would be impossible. So as I told, it is a transistor level circuit design. So multiple billions of transistors will be built inside the Tanner tool. So it's a Siemens tool. Similarly, we have tools in Cadence, Synopsys, various other companies are also available. So this is about the basic understanding of EDA. EDA is nothing but electronic device automation tools where you will do the transistor level design. Tanner, you can perform analog mixed design flow and also you can perform analog design. Analog mixed design in the sense it's a complete application level. Mainly that will be performed in the industry level. What they will do, they will build a physical design and similarly, alternatively, they will be doing with the digital design also. Once both are completed, they will do the mixed analysis using the caliber verification. So that is a complete different path. But as a freshers, analog mixed signal is not necessary. So if you know about the basics, like whenever you want to enter into the core domain, that too for the ASIC, you should be thorough with the basics. Like you should be knowing what is CMOS in your like CMOS circuits and some P substrate, in substrate, and various electronic things. Like you should be also knowing about the resistors, capacitors. Even basic things will count whenever you give the interviews. They will be not asking you to the top level, but they will judge whether your basics is stable or not. That is how they will conduct the interview. And knowing about the tool is more than enough. Like inside the tool, if you know how to work on that, like whenever you enter the corporate, you'll be having the trainings. Easily you'll get to know that. Easily that is not an issue. So moving further, here I have given the differences between the ASIC and the FPGA. So ASIC flow typically goes from RTL. So in case in ASIC also there are two different flows. Either you can perform digital design and verification, and you can perform analog design and verification. For the digital design and verification, we call it as a semi-custom design flow. And for the analog design and verification, we call it as a full custom design flow. Full custom design flow is the analog design and verification. Semi-custom design flow is the digital design and verification. And ASIC flow, I have just given the flow, like what we will do the first. There I have mentioned the semi-custom flow. First, we will use the RTL. I think RTL you all will be knowing. RTL is a registered transfer level. And under RTL means you should remember HDL, hardware description language. And under the HDL, you have three languages. One is Verilog, and one is VHDL, and another one is a system Verilog. So then using you can write code in any of the languages, whichever you are capable of. And once after writing the code, you will perform the synthesis. In the synthesis, the correctness of the code will be measured and the gate level netlist will be formed, everything you can observe. Once the synthesis is done, you will go for the placement and routing. Placement and routing in the sense, it will form a layout. And once the layout is formed, you can go with the physical verification. For this physical verification, again, you will go with the caliber. In caliber, you can do the digital design verification also, analog design verification also. Finally, it is one of the verification tool, and it's a very industry standard tool. Even if the people who are using the cadence tools, even they will integrate caliber with the virtuoso tool for running the verification. Like if you browse about the caliber, you will get to know it's a very industry standard tool. Mainly, why we will do the verification is, for example, you have some requirement and you will design some silicon. What you will do, you will design the circuit and then you will build the layout for that and you will generate a GDSI. GDSI is nothing but a graphical design. Once the graphical design is ready, you will take it to the foundry for the tape out, for the fabrication part. But you cannot take it to the fabrication directly without verification. So there are various foundries available, like Intel foundry, Samsung foundry. So they will be having a certain rules for each foundry. If it pass the certain rules, then only they will take your whatever the GDSA generated and they will form a tape out. Or else it will be uh, like they will verify and then if it is satisfied only, they will do the fabrication part. So under the verification, we have three different things. One is design rule check, DRC. Second comes the layout versus schematic. Third comes the parasitic extraction. So DRC is like whether the minimum width is matching, spacing is matching. So each, like it's not like there are 10 foundries, means 10 foundries will be having a 10 different set of rules. If it satisfied with the Samsung, then it is not like it will satisfy with Intel also. Each will be having different spacing, various things will be different. And here in the Tanner tool, we have a rules file already readily available. That is mainly for the academic purpose. So whatever the design you will do the verification here also. If it passes the verification, it's not like it's ready for the foundry tape out. Because the set of rules which is given here, it's a very lower level. Like it's not into the industry oriented. So industries will be having a different set of rules and different DRC check where it will run multiple design rules. Here there will be a limited one. Here just for your understanding and to go with the flow. When it comes to the industries, again there will be a different scenario. So that is how we will do the DRC check. So DRC check in the sense, you can just take an example of some building. Once the building construction is done, there will be a site engineer who will be verifying whether the construction is proper, whether the rules what they have set in the beginning, whether it is matching. That is what DRC. Like minimum space is given, width is given, whether everything is set properly in the proper corner. Everything the DRC will measure. Next comes the LVS, that is a layout versus schematic. Layout versus schematic means like whatever the netlist generated, that will be taking into the layout SDL navigator. SDL means it's a schematic driven layout. Like it might be like overhead for you, like I'm telling everything in a single go. Like while performing the demo, you will get into it, what we have explained now. So it has to compare whether the layout is matching with the schematic which I have done. So it will undergo the differences, like layout versus schematic will be performed. So you can just take an example of same construction of the building. Before construction, you will get a blueprint, right? Once the blueprint is ready, the construction will go on. Once the construction is done, the site engineer has to verify whether the blueprint is matching with the construction which is designed. So it's nothing but a LVS. Whatever the blueprint was there, like you can take schematic which you have designed is a blueprint, and the verification one layout which you have formed is a building. Whether the building is matching with the blueprint. This is what the LVS will compare. That is the layout versus schematic. And then comes the parasitic extraction. So PX in what it will do is it will extract your resistors, capacitors, coupled capacitors, whatever it is utilized, it will extract and it will show how many like and spice file will be generated. So beginning what you will do once the design is done, you will perform the simulation. Once it is a pre-layout simulation. And once the layout is formed, GDSI is generated, you can do the post-layout simulation. Like it's not necessary, required. Like when it comes to the academic part, here it's not necessary. But in industry, they cannot send it for the bulk production without verifying the multiple things, the process which they have to carry out. So what they will do, they will generate a spice file using a PEA, and that they will take into the post layout simulation. Again, they will go to the TannerEda, and there they will perform the post layout simulation. They will add that spice file, and again they will rerun the simulation. That is how the post layout simulation will work. Similarly, we will be having the RVE directory also. That's a result viewing environment where the result will be found. So this is about the complete verification part. I have a flow chart. I will just explain you. So you will get a clarity, like whatever I have told now, you will get a clarity once you see the flow chart. So here just you can observe like how the ASIC flow and the FPGA flow has a difference. In ASIC, what we will do, the code will be written in a RTL, and then it will perform the synthesis, and the placement and route will perform, and physical verification. Physical verification using a caliber tool. It comes with the ASIC part. When it comes to the FPGA flow, here you can take, there are various companies. Like we are authorized for the AMD Xilinx and AMD FPGA. Similarly, we have Microchip, we have Intel and Texas Instruments, various companies are there. So here what we will do is we will write the RTL code, and it's the complete digital part. It's a field programmable gate array, and nothing like verification, everything will come into picture. Even here in the ASIC, you will not use any hardware. It's complete the software oriented. You will just verify everything through the software, no hardware come into picture. When it comes to the FPGA, you will be having the FPGA hardware in your hand. So once the synthesis is done, implementation is nothing but a placement and routing. Implementation performs the place and route itself. Like whatever the hardware you have configured, inside that whatever the resources will be there, based on the code which you have written, it will do the placement and routing inside that whatever the resource available, and it will give you the utilization. For example, do you know about the FPGA resources and all? Have you studied 7 series architecture? You're not aware. Yes. Okay, like I'll just give a small overview. In FPGA, we have various architectures, 7 series architecture, and SOC. SOC is nothing but a system on chip. Like some will be having a processing system and a programmable logic. It will be a combination of both FPGA boards. Some will be only the programmable logic board. And when you, when you hear that FPGA, inside the FPGA architecture, there will be DSP slicers, there will be a lookup tables, there will be CLBs, configurable logic blocks, and under that you will be having IOs and inputs and outputs. Various things will be coming. Like these are all the resources available. So when you have some FPGA board, that FPGA board is comprising of all that resources. Whenever you're doing a placement and routing, whatever the code which you have written, what are all the resources it wants to take from that particular occupancy, it will go and do the placement and routing inside the hardware. That is what the implementation. And once the implementation is done, you will do the bitstream generation. Stream is you will be having a certain different boards. Each different FPGA boards will be having a different constraint file. We'll call it as a Xilinx design constraint file. Like in that constraint file, whatever the board you are having in hand, like for example, you can take switches, LEDs. Each different will be having a different pins. So the software should understand which is the pin I'm going to bitstream, because you are dumping your program into the hardware, and the software should understand where I have to dump my code into the hardware. So you will be doing the constraint using the pin numbers. Once the bitstream generation is successful, you will load that into the hardware and you will verify. For example, if you take counter code, there will be 4 LEDs. What you will do constraining for the 4 LEDs, and you will use some 2 switches for the reset and up down, and you will run the up down counter. Where in the LED you will get the output. And again, the clocking will come into picture there, because counter is a sequential circuit, and clock will be like a very high 125 megahertz will be the clock ratio. So if you want to, again, for example, if you're running counter, it will be not visible to your eyes whenever there is a high frequency. For divide, then you have to divide your clock. Clock divider will come into picture. Again, clock divider will be, you can do using the RTL coding. You should be knowing RTL logic. You should be knowing how to write a RTL logic in a very long. So for dividing your 125 megahertz clock to 1 hertz, that and all you can perform. And even there will be IPs available inside the Vivado tool. Like that's a AMD Xilinx software, Vivado. IPs will be available, clocking wizard IPs. So if you use that IPs, that will only convert your 125 megahertz clock to some 10 megahertz. Or else you can use your logic. If you're very good in a programming language, you can write your logic and you can divide your flow. That is how that bitstream works. And some of the features I have given here. ASIC is a application specific integrated circuit. FPGA is a field programmable gate array. And when it comes to the custom hardware, as I told, ASIC will be designed for one specific application. And when it comes to the FPGA, it's a reconfigurable hardware. So, like to make build some multiple applications, and your requirement will be having certain things. That FPGA will be having the various resources. You can take that board and you can use that for reconfiguring it to multiple applications. Not built for only one certain application. But ASIC is built for only one certain application. So it's like if you want to do analog design, it's only the analog design. You cannot do other multiple things. It's a custom hardware. Just you can call it as a custom hardware. But FPGA is a non-custom hardware. It's a reconfigurable, which you can reconfigure using the hardware description language. This difference you should be knowing. ASIC is a custom hardware. FPGA is a reconfigurable hardware. And when it comes to the speed or power, ASIC is very optimized because you will be building that for only one certain application. For example, you're doing some PhD, you'll be having some power analysis which you have to carry out. So you will be getting the you are only designing the circuit. For example, you will be designing the circuit concentrating on only power analysis. You will not concentrate on any voltage or any other efficiencies, other parameters. You will not at all look into it. Your concentration will be only for the power. So it's a mainly built for one particular thing. So it will be very optimized because since you're working on one particular scenario, you will make it is more optimized. So it will be very optimized when it comes to the speed or power. FPGA is slightly less optimized because it will be ready to use for multiple applications. It's not only for the power. It will be designed for multiple things or multiple parameters. So it will be slightly less optimized. And when it comes to the cost, ASIC will be high ratio because here you're doing a transistor level design. Once you do the design, you will do the verification, you will send it for the tape out for the fabrication. And when it goes for the fabrication, they will not do the fabrication directly once the verification is done. Then it will undergo the DFT test. I think you all have heard about the DFT tool, device for testability. So why the DFT tool is necessary? Whenever some circuit you have designed and the tape out is ready, before it goes for the bulk production, what they will do, they will undergo the DFT test. That is the device for testability. And here we have a tool called a test. There is a command line tool. You should be knowing the Linux command. You should be thorough with the Linux. It's not a GUI. Graphical user interface will be not present with the test tool. That is how you will use the test. So ATPG, various things will come into picture. Like if you want to learn about the DFT, there is a subject called testability for VLSI. If you go through that, you can like stuck at 0, stuck at 1, like various things will come into picture. It's like a depth concept. If you're interested in DFT, there are various vacancies outside in the market where you can directly go as a validation engineer, like a DFT engineer. We'll call it as a validation also. Like what you will do at the end of the day, you will design, verify, and then you will do the validation before the bulk product. That is how it will go. So why they will do all these tests? Because if they do the bulk production and if there is some hardware issue, it will be like a waste of cost. Bulk amount of money will be wasted. So before the bulk production, they will carry out all these procedures in the ASIC. But FPGA is not like that. It's a reconfigurable hardware. If one application doesn't work, some other will work. So it will be specifically built for various applications, and you have to bring up the board based on that. And low cost of the FPGA will be less compared to the ASIC. And use case. ASIC is a final chip product which you are starting from the beginning. You are building the chip. Complete chip is built from the person who are working on that particular application. FPGA is a prototyping. Prototyping in the sense the chip is ready. Someone has given you the chip. Just you are using that to build some application. It's not like a chip product. It's a reconfigurable hardware. So this is the difference between the ASIC and the FPGA. I hope you got some idea regarding what is ASIC and what is FPGA. So moving further, so here I have given the TannerEda. Like Tanner is an analog and mixed signal design tool. So here you can perform complete analog design and analog mixed design, and you also can use it for the MEMS. MEMS in the mechanical system. So MEMS is nothing but it's completely a mechanical part. And here you will not use a SEdit for the MEMS. For the MEMS, you will use the LEdit, like where you will be building your layout. Like for some example, you can take accelerometer and all. And that again, you cannot perform the MEMS application directly using a Tanner. Again, you should be having some ANSYS tool. MEMS, as the name specifies, is a mechanical. Mainly, it comes into the mechanical background. So here you can build the layout. Once the layout is built, you have to integrate the Tanner with some ANSYS simulator. Inside the ANSYS simulator, you have to simulate that, first, verifying the layout is proper and it is functioning according to your specification. Here, you don't have any simulator to run the MEMS design, but it has a feature MEMS which you can design using the layout. That is a LEDit part. In SEdit, you will not do in a LED. So in a Tanner, I will just tell about that. Here you can just see what I mentioned. Tanner is a full flow analog. It's mainly for the full custom design flow. And here mixed signal design environment also can be performed. Used for the schematic capture. Schematic capture in the sense, you will design your circuit, like the schematic will be designed. And that schematic you will do the simulation. And once the simulation is done, you will generate a netlist file, and that netlist file you will take to the LEDit inside the HDL navigator, and you will form the layout. So it's a strong in transistor level circuit creation. So it's a transistor level. It's complete ASIC, transistor level creation and verification using the caliber. And it's perfect for analog and mixed analog digital chips. And when it comes to the key modules, what are the things Tanner is having is SEDIT, Spice, LED. SEDIT is a schematic capture where you will be drawing your circuit. T-Spice is an analog simulation. Once you run the simulation, again I want to tell other features which are available in the Tanner. You have T-Spice, you have Endo, and you have AFS. AFS is a analog fast simulation. So you can just take a difference. So T-Spice is mainly used in the curriculum wise. Whenever you're doing academics or when you're doing the very small project, that simulator is more than enough to run your simulation and to give you the waveform. But whenever you go for some higher end design, higher complex simulation you want to perform, you will not go with the T-Spice. T-Spice will be very lower simulator tool. So instead of this, just you can consider T-Spice. It's a simulate. Similarly, Eldo is a simulator where you will use for the complex design. And now we have an advanced feature called AFS, analog fast simulation. So it is mainly used in industry level for the fast analog fast simulation. So these are all the three things. Just you can consider T-Spice is the basic simulator, Endo is the moderate simulator, AFS is the high level simulator. All are the simulators for doing the verification. So here you will perform the analog simulation and Spice engine like DC, AC, various analysis will come. Transient analysis, DC analysis. Mainly we will do the transient analysis for the timing. Like if you want to check the voltage general DC analysis, sweep analysis, various things you can perform. That and all, just you give the values and you can run and verify. Various analysis you can do. And once the T-Spice is done, another feature we have is WEdit. That is a waveform edit window. So once the T-Spice is satisfied, like your design is proper and if the simulation is run successfully, the waveform window will pop up directly where you can observe your waveform. Like it will show the functionality. For example, if you take some AND gate or NOR gate, you can verify using the truth table. Like in AND gate functionalities, whenever it is 0, 0, it will be 1. Whenever 1, 1 also it will be 1. 0, 1, 1, 0 will be. Similarly, you can verify the functionality. LED is for the layout editor, for the transistor or IC layout. In LED, what you will do, you will take the netlist, like in the T-Spice, you will generate a netlist. That netlist you will take to the LED in the HDL navigator, and PMOS NMOS will be readily formed. Here you don't need to do your stick diagram from the basic. Substrate is not required to form from the beginning. Directly the PMOS NMOS will be ready. You have to make a only internal connection, like input connection, output connection, VDD connection, and the ground connection. Just you want to make that connection, like poly layer, metal layer connections you will do. And whenever you want to connect poly and metal, you cannot connect directly. Again, we have another layer inside the layer palette. You will be having a via option. There will be having a contact poly. You have to use a contact poly to make a connection between the metal layer and the poly layer. That connection you have to do, and then you will be completing your layout. Once the layout is done, you can export the GDSI and you can start the verification. And in the verification, you can first run the DRC. There, any width issue or a spacing issue, if something is overlapping, everything it will indicate where you have to debug and resolve. So you will get to know, like there you will get errors. If you right click on that, it will highlight in a red color inside the layout. There you can go and verify what are the issues which is showing, and then you can sort it out. That is how the DRC will work. Once the DRC go with LUS, and then you go with the parasitic extraction. So that is the caliber one with Tanner, physical verification. What? Yeah. Here, like inside the caliber, we have uh, LVS, we have DRC, we have XARC, we also have RVE. RVE is nothing but a results viewing environment. For the analog design using a Tanner, this is more than sufficient. Doing the DRC check, layout versus schematic check, and the parasitic extraction. Other exact, like for the current voltage execution, multiple things will be, which is not required here, which you will be using for the analog mixed design flow verification. And even as I told, caliber can be used for the verification of digital design also. Like where the once after the synthesis and placement and routing, placement and routing will be having the direct connection to the caliber, where you can directly launch the caliber inside the placement and routing tool, and you can run the verification for that particular aspect. You will work. Like there are various features. Like there will be limited features used for limited tools that you will learn. Like once you work on the tool, and if you browse also, you get the various information. That is how that caliber will work. Yeah, there will be multiple options, but you don't think about all that. Mainly, you concentrate on what has to be done for what. Then you can further move. And here I have given about the caliber. So this caliber is the industry standard physical verification tool used after layout to ensure the design is manufacturable for the form piece. So it checks DRC as I told in the beginning. There is a design rule check, and it goes with the layout process schematic. There is a LVS and XRC, that is a parasitics for the accurate timing and work. As I told, parasitic extraction is for the timing. You told about some PSRC, that is for some current or voltage, something you will come. Various things you can perform. Like each will be having a different path, like one for DRC, one for parasitic extraction, layout, current, various things will be available. RVE, there's a result viewing environment. Once you run the DRC, 3 to 4 windows will open. The command line, whatever it is happening, it will just show whatever it is running. That and all you can observe. And why this caliber is important? Caliber ensures the layout matches the schematic electrical and meets manufacturing rules. As I told before the production, it has to meet the manufacturing rules, and which prevents the costly silicon failure. Silicon is too costly, right? Like if it fails, it will be a huge loss. So they will follow all these procedures. So which prevents the costly silicon failures. In the verification, you get to know whatever the issues you are getting, so that you have to debug and resolve the issue. So this is about the caliber physical verification. Here I have given the full custom design flow chart. So first we will start with the physical design using a Tanner tool, and then we will go with the physical verification using the caliber tool. And then if you, as I told, the parasitic extraction will give you the spice file, which you can use it for the post layout verification, which is not necessary here. It will be used only in the industry level. Like they want to take it for the tape out, so they will be moving for that particular aspect also. Just for your understanding, I have added this part also. And once after the post layout verification, tape out will be ready. That tape out you will take for the IC fabrication. Once one chip is fabricated, it will go for the IC testing. IC testing is nothing but DFT, device for testability. IC is integrated circuit. So this is the IC full custom design flow. I have given in the next slide, I have given a complete overview, like how the full custom design flow is performed. I told you about the two things: full custom design flow, semi-custom design flow. Semi-custom design flow is a complete digital part where you will perform read the RTL code, and then you will do the synthesis, placement and routing, and then verification. And this is a full custom design flow where you will design the circuit. It is a circuit level, transistor level. You will do the analog design, analog simulation, analog layout formation, and the verification. So you got to know, right? Like in the Tanner we have SEdit, TSpice, WEdit, and LEdit. And in the Caliber we'll concentrate on DRC, LVS, and EA. So here the schematic capture first thing, that is the SEdit, schematic editor. SEdit is nothing but a schematic editor. And then we will perform the analog simulation, which will display the netlist file using a TSpice. And again, in the analog simulation, you can use different simulators, ELDO, AFS, and TSpice. We will concentrate on TSpice for the academic purpose. If you want have some complex design, for example, we for inverter and these circuits is more than enough with the TSpice. If you're going for some common source amplifier, if you're going for some op-amp operational amplifier, some if you are planning to design some static RAM, then you can move with the ELDO. AFS is not necessary, I guess, like because it's a complete industry level. Whenever they're running some industry-oriented things, it will be useful. And as I told, mixed design flow you can do here. Even for the mixed design flow, AFS will be better because it will do the analog fast simulation. As the name indicates, AFS is the analog fast simulation. So next comes the physical layout. That is a layout edit where we will take that netlist formed in the uh, TSpice, and we will form the layout so that PMOS and NMOS will be present, and then we'll make the internal connection. So that whatever the netlist is, we'll get through the SEdit. In the SDL navigator, we will add. SDL navigator is nothing but schematic driven layout. That is the SDL router. And then once after the making connections, we'll perform the physical verification and finally take out. In case necessary, post layout simulation will be done next to the physical verification. So this is the complete full custom design flow. I hope you got an idea on this. So manually you can do. You have to form the substrate level. Substrate in the sense, again, you have to know the complete stick diagram. You have to take P well, N well, design the complete thing. So if you want to design some AND gate, NOR gate, or inverter also, it will take 1 day. Because you have to make all the connections. You have to first make the PMOS, and then make the NMOS, and then you have to make the internal connections. And then finally, you will go with the verification. But if everything is ready, why you want to do from the beginning level? Now you have a chat GPT and everything. Like most of the case, you'll be using chat GPT. So similarly, when some ready thing is available, not necessary to go and again dig with a basic level because there's a time killing process. Even if you go to the industry, you will be having certain options. And here we don't have a routal options. Like whatever the connection I'm telling you, have to make the internal input connection, output connection, VDD connection, and ground connection. There is the option called route all. Even this was present in the Tanner previously, 5 years back. Now they are giving that option only for the industries. For the academic, they have removed them. If you have that route all option, even that connection is not necessary. Once you load the HDL navigator, it will give you a ready layout. Just you want to go to the verification. No connection, nothing. Any errors if it is showing, then that might be the errors in the netlist formation. So here at least you will get to know how to make the connection. If everything is ready, then also it's the problem. Like you will not get to know the basic of whatever the connection you are doing. So substrate level is not necessary. I think if you are from the electronics, you would have studied VLSI subject where you had some VLSI lab. There, micro like most of the colleges they will not use the industry tools. They'll use open source like microwind, LT Spice or some tools. There and all you have to form the complete substrate level where you will design your complete P well, N well, everything you have to see the spacing, width, overlapping. It's like time killing. It's a very time killing process. So I think it's better to go with this. But you can do the substrate level if you want to. You can try that. Questa Sim. Questa Sim is not it's a complete digital design. So I will tell you about it. So whenever you're working, you concentrate on one particular domain. If you mix analog and digital, again it will be confusing. So either you choose a ASIC or either you choose a FPGA. Like Questa is not like a FPGA, but it is a digital tool. It also works with ASIC. And Questa, you can just tell it as a universal verification methodology tool. So whenever you have some very big code, you know about the code coverage and all optimization. Whenever you want to optimize the code and when you want to check the code coverage, Questa is the number one tool where various DRDO, ISRO, and AD, various labs they are using that particular tool. When they add the very complex code, which is the design code, within half an hour or 45 minutes, it will give you the complete optimized result, which will take more time in the AMD Vivado tool. It may take some 6 to 7 hours. That 6 to 7 hours time consuming optimization can be done within a half an hour. It's a verification, simulation and verification tool, which gives you the optimized result with the code coverage. Here we'll go with the question symbols. So this is about the full custom design flow. And here I've just given the CMOS basics. I think you all will be knowing about the CMOS because many of you people are from, huh? Yeah, since everyone are from, I think everyone are from electronics domain. Okay. So nothing like you should be whenever you enter into the ASIC domain, you should be knowing what is MOSFET, like what is NMOS, N channel, P channel, what is CMOS. Under the CMOS, you'll have having a NMOS and PMOS. That is what I just mentioned here. MOSFET are the basic building blocks of modern digital and analog circuit. For the both analog and digital, it's a basic building block. Like you can take consider it as a brick when you're constructing some house. The main necessary thing is a brick. So MOSFET is nothing like a brick. Without having the brick, you cannot construct the building. Without knowing about the MOSFET, you cannot move with analog thing. So that is what the MOSFET. And MOSFET has four terminals like gate, source, drain, and the body. That is the internal connections for the input, output. Various connections you can do using a MOSFET. And current flows when a voltage on the gate controls the channel. So this will be everything will be controlled through the gate. And there are two main types. That is NMOS and PMOS. NMOS is a N channel, P channel. So you can see it turns on when gate is high. The difference between NMOS and PMOS is NMOS turns on when the gate is high. PMOS turns on when the gate is low. So these are the complete basics. There are multiple things in the basic. Like if I start telling you about the electronics, I can tell for 1 or 2 days. And the only basic things. So it's a turns on when gate is low, and CMOS is a complementary MOS. So it's a complementary MOS. Use both like CMOS, NMOS and PMOS are derived from CMOS. Under the CMOS, you have PMOS and NMOS. Use both PMOS and NMOS together in a complementary fashion. So as whenever you design the circuit, PMOS will be in upper level and NMOS will be in a lower level because PMOS is a pull-up transistor. NMOS is a pull-down transistor. So logic will be high for the PMOS, logic will be low for the NMOS. So this arrangement gives you very low static power. Like there will be no DC current at all, almost no DC current, and whenever the switching is not done. And this reason, nearly all digital chips today use CMOS technology because of this particular aspect only. Modern technologies are using this CMOS as a brick, like it's a with a PMOS and NMOS. This is about the basics of PMOS and NMOS. So, and the schematic design of CMOS circuits. I've just given A schematic diagram is what is schematic diagram is nothing but it's a symbolic representation. When it comes to the RTF, you will be writing your code. Coding is a complete coding thing. Here it is a complete schematic drawing, symbol representation. So there will be a various PMOS, NMOS, and ground, VDC, VPulse. When it comes to the electronics, inside the libraries, there are various things available. Using that, you will do the symbolic representation. You will do the circuit designing. It's nothing but a circuit designing. When it comes to the RTL, it's nothing but a coding. And which transistor connect to which signals, that you will just see, and logic function of the circuit. And whenever before any layout or physical design, you first design the circuit logic. Like if you want to go with the layout or physical design, like physical design and verification, first thing what you have to do is you have to go with the design only. Once after designing and getting the simulation and netlist file only, you can go with the layout part. So you first design the circuit logic, like how the things are connected, like how you will make the connections in a transistor level, that is using the CMOS. For example, if you take a CMOS inverter, NAND, NOR, you can go with the AND gate, OR gate. You can go with some flip-flop, sequential circuits. Various things is possible. Again, you might be knowing about the difference between the sequential and the combinational circuit. Sequential is a circuit which is having a clock. Combinational circuit doesn't have a clock. It's the main difference. And this schematic is a functional blueprint. Will be later translated to the layout. As I told, it's a blueprint which will go take it to the layout as a netlist. So this is not into the complete tools. I am just giving a overview of the basic of electronics. This is not related to the tool. Just I'm comparing this how it will be related to the EDA. So today we'll be performing the basic. We'll start from my inverter logic circuit. So in inverter, what we will use for the inverter? We'll use PMOS and NMOS. As I told, PMOS is the pull up transistor. NMOS is the pull down transistor. You just make a connection. What and all are necessary for making the inverter? PMOS and NMOS are necessary. Other than the PMOS and NMOS, we have to give the input. We have to provide. We have to get the output to check the functionality. And together with that, we have to give the voltage. Voltage can be given using VDC director. And we will give the V pulse. In V pulse, the voltage will be transferred. Like a VDC mainly will connect it for the VDD. V pulse will connect for the input. And similarly, we can give VDD also. VD, after making a VDC is not necessary, but if it you give also, it's not an issue. Like it's based on your circuit design. Like however you want, you can design. Some will use VDD and VSS instead of ground. Like just will add the VSS. You can even add ground. Like you can generate a netlist. Inside that, what you can do is you can write the truth table. Like for the digital design, what you will do for the simulation purpose, you will do the write the test bench instead of forcing the values manually. If you want, if you don't want to write a test bench, even you can force the values inside the simulator also. But you can see one output at a time. Similarly, here also we can form the test bench also, or else directly also we can simulate. That I will show you while performing the demo. So we'll perform the simple transistor level. Here we'll make the connections. And for example, if you want to do some NOR gate, in NOR gate, what you have to do, you have to see the functionality. Functionality, if you want to check, there will be two inputs, VA and VB. So what you have to give, you have to add the V bit. V bit is the it will provide you the sequences. Like it will be having 1101. You can change the sequences. So for the you will add V bit for input A and input B both. And once you run the simulation, you'll get a waveform based on the bits you have run. So you can verify your waveform. And inverter functionality, you all will be knowing. Whenever the input is high, output will be low. Whenever the input is low, output will be high. That is the what functionality it should satisfy once after running the simulation and after getting the graphical waveform. So moving further, this is about the stick diagram. As he was telling, if you want to form the layout from the substrate level instead of root all option or directly loading through SQL navigator, you should be knowing the stick diagram concept. And again, it's a depth. So here you should be knowing the detailed layout creation and stick diagrams where you will do everything hand drawn using the CAD. And here you can see what stick diagram mainly shows. Like there are intermediate step between the logical schematic and the full layout. Whatever the stick diagram, it's an intermediate step we should be knowing. It is between the logical schematic and the full layout. So whatever the logical schematic is formed, based on that you have to build your layout. So it will be an intermediate step for that. So what stick diagram mainly shows it's the layers and the connections. Here you should be knowing what is a diffusion region, what is a polysilicon gate, what do you mean by metal interconnects, and what are the contacts and vias. As I told, via we have contact. When you want to make some connection between the two different layers. You should be knowing what we have to add between that, because if it overlap, it will give you the DRCL. So it's like a complete basics of stick diagram you should be knowing. I think in a VLSI subject you would have had that, where you learned all the basic things. And transistor are formed when polysilicon crosses the diffusion. So polycrossing N diffusion NMOS, it will you can take the example of polycrossing N diffusion for the NMOS and polycrossing P diffusion for the PMOS. So these all things you will be knowing, like stick diagram. But it is not necessary. But as the if you want to attend the interviews, then the scope of the okay. Hmm. Color, yeah, polymer substance. Like if they know all that stick diagram things, it will be helpful for the interview purpose, because that only they will ask. So these are all some of the rules of the stick diagram, what I have mentioned. Like what you will see, like whenever you want to build the layout from the substrate level, you should be knowing if two sticks of the same layer touch, electrical contact will happen. So these are all the some of the rules which you have to follow while designing the layout. And if different layers cross without a contact symbol. So as I told, there are two different metal layer and the poly layer. If it crosses without any proper contact, so it's like no contact. So you have to add the contact layer for that. And PMOS devices are drawn above the CMOS midline and NMOS below, because PMOS is a pull-up transistor, NMOS is a pull-down transistor. And VDD and ground rails are drawn horizontally with signals connected using vertical sticks. So these are all some of the rules of the stick diagrams. So here I have given how this stick diagram relates to the Tanner and caliber. So in Tanner, you will capture your circuit schematic where you will design your transistor connection and simulate behavior at electrical level. And once the simulation is done, when moving towards the physical layout, you will be knowing the concept of the stick diagram, and you will be stick diagram gives you a mental and a visual framework, so that how to plan, how to devise, how to make the connections, everything. And caliber then verifies your detailed layout meets. Whatever the layout connection you have done, it will verify the complete layout meets all before the manufacturing. Whatever the DRC manufacturing companies have set of rules, that it will verify, and it will check for the layout versus schematic also. And what you will do first is schematic you will draw, and then you will go for the stick diagram concept, and then you will form the complete layout, and then you will do the caliber sign off. That is the verification part. So this is the complete full custom design. So like you were asking about the Questa sim. So I just mentioned about the Questa sim here. This also will be working on today. Questa sim is a simulation and verification tool. Mainly, you can call it as a UVM tool also. UVM means universal verification methodology. You can use Questa sim for the writing the system Verilog codes. Yes, will be having a OOPS concepts also, operational like object-oriented programming concepts also, and where you can perform some assertions. Various things will come into picture. So again, it's a different verification. Like we'll be having certain roles for the verification also. So this question sim, as I told, mainly it will be used in government labs, most of the government labs, for running their application codes. So QuestaSim is a mentor advanced RTL simulator and verification environment. Here you can compile your code, you can do the simulation, you can do the optimization, you can do the code coverage, you will get the FSMs, finite state machine, you might be knowing, Mide and More models, you will get the FSMs, and you can get the RTL blocks for the code which you have written. Various things you can perform. It's mainly for the RTL level. Like I was telling you about the FPGA, AMD Xilinx tools. If you compare it with the QuestaSim, AMD Xilinx tools, what you will do, you will write the code, you will dump into the hardware, and you will observe the output in the reconfigurable hardware. Here you don't have a reconfigurable hardware. Just you will do the simulation and you will optimize it. And in AMD Xilinx tools can be integrated with the QuestaSim tool. So here, while performing the simulation, we have a simulator called Questa simulator. In Vivado, we have Vivado simulator. You can write a code in Vivado, and I can integrate the Questa sim if I have the in this my system. If I have both the tools, Questa sim and Vivado, what I can do is I can integrate it with Questa sim instead of Vivado simulator. I can use the Questa simulator for running the simulation. So most of the integrations are also possible. So here, as I told, you can perform assertions, and you can perform coverage, and you can perform the test bench you can use for the simulation, and advanced debug you can perform, various features you can perform. So where you can use it for the simulation and for the testing the logic, various things you can do using the QuestaSim. So this is about the QuestaSim. I hope you got an idea. It's a complete RTL simulation and a verification. And I think you all saw about the catapult also. Like I will not giving any training about the catapult, but I will tell what is catapult. Catapult is a tool where you can convert your high-level language into the hardware description language. For example, there might be some computer science engineer who is not aware of any RTL thing. What he can do is he can write the code in a C and you can form a RTL. And that RTL code which is formed, he can directly take it to the Vivado. And then he can create an IP. Similarly, like the replica of Catapult in AMD Xilinx, we have a tool called Witty's HLS. It's a high-level synthesis tool. Even Catapult will call it as a HLS tool, high-level synthesis tool. Why this high-level synthesis tool is used is because mainly the purpose is to convert your high-level language code into a RTL language. That is a C++ code into Verilog or VHDL. And then you can integrate this Catapult with various other company software. Like you can integrate with the Vivado tool. You can integrate it with a system. Like it will be having the option to select the FPGA hardware. Like if you use Vivado, you can integrate with AMD Xilinx hardware. If you integrate microchip, you can integrate with the microchip hardware. If you use Intel tool, you can integrate with the Intel hardware. So it is giving you an option to integrate with the hardware and you can execute the synthesis and all. So Catapult is mainly for the conversion. And similarly, you have a tool called Aprisa. Aprisa is a very new tool which has been formed recently. Aprisa is mainly for the placement and routing. You can use it for the placement and routing. It's like released 4 months back. Like previously, we were having a tool called Oasis and Nitro. Oasis was the synthesis tool, and Nitro was a placement and routing tool. And inside the placement and routing tool, that is the Nitro, we have an integration of Caliber for performing the verification. Even Aprisa will be having. Even I am not aware of the Aprisa because still they are not trained us also on Aprisa. It's a very new tool. In the future, you can use it for the placement and routing. Other than that, which are the tools you have? There's the PCB tools you have. There's the expedition and the hyperlink. So these are all the complete PCB design tools where you'll be doing the board design mainly. Like a PCB means it's a printed circuit board. Again, that will be covered by some other person. Like I will be taking a one-day training after the installation part. So these are all the some of the tools which are available in the complete EDA. So mainly today we'll be going with the Tanner, Caliber, and QuestaSim. Tanner is a physical design tool. Caliber is a physical verification tool. QuestaSim is a functional simulation and verification tool. Similarly, PCB tool we have Links and Expedition. High-level synthesis tool is a Catapult, and placement and routing tool is a Aprisa. Similarly, older tool was Oasis and Nitro, that is for the synthesis, Oasis and Nitro for the placement and routing. Now we have Aprisa. So these are all the various tools which are available, and DFT for the device for testability. Tessent. Tessent is a command line tool. So in this, whatever the tool I explained, all the tools can be used in Windows and Linux both. But Caliber and DFT tool, these are command line tools. You can use Caliber only in the Linux systems, not Ubuntu, only CentOS or Red Hat. Red Hat is a specified version. We'll not tell about the CentOS, but you can use in CentOS also. So I took more time to bring up the system for working with the tool. In DFT is a complete command line. You will not get any graphical user interface. Everything should be run through GUI, command line, not a GUI. In Caliber, you can integrate it with LEdit. In the LEdit only, you will get a window to open the DRC, LVS, and PX. Directly, you can integrate and you can run. In case if that integration doesn't work, you can launch separately in the command line and you can use that. You will get a GUI. But you will be using it in only Linux systems, but you will get a graphical user interface. But Tessent, you will not get a GUI. It's a complete command. And if you want to learn the DFT, you go through the testability for VLSI subject. Without that knowledge, it's very difficult to go with the DFT. You should be knowing like what is ATPG, various concepts will come. You can go with that. So these are all the basic explanation of what are the tools available, what are the flows. And here I told about the two flows. There's the full custom design flow, semi-custom design. Full semi-custom mainly digital design and verification. Full custom design flow is the analog simulation, analog layout formation, and the verification. It's a complete Tanner and Caliber flow. It's a full custom design. So this is about the theoretical part. Like there are various things to tell, but we don't have a time. So I will do one thing. I will share you one small PPT. Like I will share the PDF. We can't share the PPT. So I will share with the Prashant bro. So you can like in that I will include like what are the caliber verification, what do you mean by LBS, what is DRC, what is PX, why will perform with some graphical orientation so that you will get a clear idea. You can just so we'll have a lunch and we'll start with a demo part. Like we'll have a demo in the classroom itself so that we'll do a hands-on. So I'll just guide you so that you can follow the steps and we'll complete the complete flow for the questions in my uh, this one full custom stuff. So for both for the questions in Tanner and Caliber. And once you know how to I think it will be new for you to open with the Linux systems also. I'll guide you what are the commands and how to launch the tool and what are the invoking commands. Once you get to know that, you can do some basic design. Once the basic design you have done, you have ODT access, I guess, on-demand training, where multiple students are working on that. So since you have that all access, you can start some application level designs. By going through that, if you know the flow, you can perform various things. Practically, if you implement, then you will be thorough with the concept. Without practical knowledge, simply just seeing the videos or going through the theoretical part, it's like a war. Just now I will be telling within 2 days you'll be forgetting. So it's a complete day-to-day workout if you do with practically, then you'll get a more idea. So you'll get a complete flow. We'll explain once after the lunch. Now we can take a break for the lunch. So while checking the DSC errors, I will get make errors and I'll show you how to solve. Can be visible at least. See, for example, when you run the DRC, you will get a output environment. You will get there. It will show you the results. The results will be marked in 1, 2, 3, 4. Various results will be marked. If you right click on that and if you click on highlight, there will be option to highlight. And if you go to the layout, region will be highlighted. Only one region will be highlighted at a time. You resolve that one, again run DRC. There are some 10 errors. You can sort it out one in a time. Like you can just observe, you can sort it out one at a time, or else you can take time to debug it. You can resolve it. Once the screen is empty with zero error, then it satisfies your DRC check. That is how it will work. You can write very long code. It's like what I didn't get your question. You can do anything. If you have a code readily written, you can copy that one, or you can write your own code, or you can copy paste from browser. If you are good at coding language, you can write your own code. It's better so that you will learn how to do the write the Verilog code kind of logic level. You can. It's better to write the code on your own. Verilog is not that difficult language. Okay. RTL. RTL is a register transfer level. Under the RTL only, the hardware description language will come. So in the HDL, we have Verilog VHDL and system Verilog, which will use it for the FPGA. In ASIC also we will use. In FPGA, almost we will use the Verilog and VHDL. And again, embedded system design, like if you I was telling about the system on chip, right? SOC. If you want to configure the SOC, it will be having a processor. Then, together with the Vivado tool in the AMD, we have VTIS tool, where you will do the embedded system design. Like what you will do, you will in the RTL level, you will write the code, you will create a wrapper for that. Like you will just take the modules, like processor modules there, and you will export it to the VTIS platform. And for that, whatever the exported thing, you will write your application using C, and you can perform the embedded. You know about the protocols. There are various protocols available. A protocol is the thing, but a communication. Like you can use CAN, you can use Ethernet, you can use UART, you can use SPI. Various options are available. That's a complete another domain. Like whatever we are speaking today, it's completely a separate domain. And this whatever now I'm telling about that the embedded design, it's a complete different domain. Like when it's come to the core department, when the semiconductor now the booming industry is semiconductor. The booming in the sense it's not like complete FPGA is booming. This ASIC domain is booming because transistor level circuits they are designing. The aim of the government is to make in India so that every chip should be designed and fabricated in India itself. That will come into picture not with the FPGA. FPGA are not designing your chip. You are taking the chip which is readily designed and you are reconfiguring it. So ASIC is the main thing which has more scope. There's a digital analog design, analog verification, and the DFT device for testability, like testing, validation, designing, verification, and validation. Mainly physical design roles will be there. And analog mix design also. Even questioning is also come under the ASIC itself. So where you will be writing the code, like complex code, you can do the code coverage and all. FPGA, under the FPGA, again you have various different tools. Like software design is there, RTL is there. RTL design means you will be using the FPGA to reconfigure the complete hardware part. And whatever the hardware part you have configured, that whatever you will create a wrapper for that, and you will transfer that wrapper to the software team. There they will use a Vetis platform for the embedded design. There C will come into picture, and then that will go for the final validation. And before that, again, we have hardware engineers, we have PCB engineers who works under the PCB designing and the layout. Hardware engineers will design the circuit. So various domains will come into picture. You can concentrate on whichever the domain you are interested to get in. There are various vacancies also. I hope you got some clarity on the concept. Hmm? R-
Yes, guys.
RISC, RISC-V processor. It's a microcontroller. It's a complete microcontroller. RISC-V processor means in RISC-V you don't have a FPGA. It's a complete processor. So in our company we have designed one board called Advik Vega. It's a complete RISC-V oriented board, which has various peripherals like UART, GPIO, CAN, like various things are available. You can perform various actions. There we have a minicom. Minicom we have it's a kind of Docker. We have developed some Docker, and inside that you can run your C program. Like we have certain programs which we have introduced. You can write your own C program. For example, in engineering, you would have done some IoT projects where you would have used some GPS, GSM, where you have connected the SIM, and finally you would have got some output or some using some external sensors, DH11, accelerometer, or any various other sensors. So there, what you are doing, you are getting the sensor separately, you are getting the breadboard separately, and everything you are getting, and just finally you are making the connection. If you have this one kind of RISC-V processor board, you'll be having everything inbuilt inside that. Even the GPIO pins are available, where you can directly make a connection and you can build your project. GPS is there, GSM is there, Ethernet is there, and you have a SIM connector. Various things are available. So this is how the RISC-V will come into picture. It's mainly the microcontrollers, mainly processor oriented. No FPGA will come. It's completely embedded system design. If you are looking for that particular thing, also we have the products on that. There's a big data. It's an Indian product. It's our first Indian product, which is designed in our company.
That is, that is
Hmm?
programmable like India.
Hmm.
Then we are going to the RV compound.
Hmm.
And we are taking that only the circuit certificate circuit. Then what is the use of the calibrate? And here is a we are seeing the output.
Mhm. In which tool you are telling?
EDS and RV compound.
Tanner only you are telling, right?
No. In the calibrate.
Caliber.
RV compound.
RV is the result viewing environment.
In that
RV is a result.
like result view pan.
Hmm.
In that we are going to check the M0 and M1 and 2, the details of the
Metal layer,
metal
whatever
layer.
is showing. So whenever you done the verification, 2 to 3 windows will pop up. In one window, the commands transcript will be running, and same window you will be getting the final result. In some window, it will be showing the error. So when you launch the caliber, you will be having 4 to 5 options. So that all options will pop up in the single go. I will tell you while running the verification in the practical part. Any other doubts? LED MEMS. It's a micro electromechanical system. I am not aware of MEMS. It's a completely different platform. As I told, you can just design the layout here. Again, if you want to simulate that, you require an ANSI simulator. ANSI simulator is required. It's an integration. Here it has a feature. Like just it has a feature. How in your vehicle there will be some extra feature. Here they have given some extra feature. Verification will be done through that.
What is the difference between this verification?
Functional. Caliber is a complete analog verification. Functional verification is for the RTL. RTL is completely different. Analog is completely different. There is a digital, it is analog. Here is a transistor level design you are doing. You are building the circuits. You are not writing any RTL code. For whatever the RTL code you will be writing, RTL is nothing but a hardware description language, register transfer level. So there you have a Verilog and VHDL code. There you will perform a functional simulation. Whenever your mind thinks of functional simulation, the functional simulation mainly comes under the digital, like whatever the Verilog code you will be writing. It's not an analog simulation. You will here in Tanner you will not do any functional simulation. It is a analog simulation. I think it's almost 2 o'clock. So 2:30. Can you come in? 2:30 will start.